So here is this matrix M that we looked at last time. And last time we found a basis for its row space. Because if you recall, M row reduces to 1, 2, 0, 0, 0, 0. And so just the set containing just the vector 1, 2 is a basis for the row space. And so the rank of the matrix is 1 because the row space is a one-dimensional vector space, vector subspace of R2. Now I want to talk about the null space. So the null space of a matrix is all of the vectors which when you multiply them, they get sent to the zero vector. So vector. And by sent to, I mean get multiplied to. So the null space of M is the set of vectors that look like X, so that M times X is equal to the zero vector. So I'm going to write down M here. M is a 3 by 2 matrix. So this is 3 by 2. So if you're going to multiply it by a vector on the right here, it's got to have two components so that the multiplication is defined. This is 2 by 1. And then the zero vector that you'd be sending to here is 0, 0, 0, 0. So we end up with a system of linear equations here. So if I perform this row by column multiplication, you do this to find the first row of this product, you're going to get x plus 2y. And then the second row is going to be 2x plus 4y. And then the third row is going to be negative 3x minus 6y. That's got to be equal to 0, 0, 0. So you get this system that looks like x plus 2y equals 0, 2x plus 4y equals 0, and negative 3x minus 6y equals 0. So if I put that then into an augmented matrix to solve it, I will have essentially gone around in a circle because I have 1, 2, 0, 2, 4, 0, and negative 3, negative 6, 0. And when I row reduce, I'm going to end up with 1, 2, 0, 0, 0, 0, 0, 0, 0, which gives me x plus 2y equals 0. So I could have gotten here just as easily by row reducing first. So instead of doing all this rigmarole with the unreduced matrix and then getting back into a matrix and row reducing, I could have reduced the matrix first, done the multiplication, and then I end up right here, essentially right away. So all of the vectors in the null space are going to look like this. So you're going to have x plus 2y equals 0. So from there you have x equals negative 2y. So your vector xy has got to look like y can be anything. And so let me call that a free variable. So I'll let y equal t. And then x is going to be equal to negative 2t. And that's so I can factor out that t. So all the vectors that are in the null space look like a constant multiple of this 2, 1. So just this vector, negative 2, 1. So just that vector negative 2, 1 is a basis for the null space. This is going to be the set that just contains the vector negative 2, 1. This means that the null space is a one-dimensional vector space because its basis contains a single vector, so that is the nullity is the dimension of the null space, which in this case is 1. So we can now find a basis for the null space and the nullity, which is just the dimension of the null space of essentially any matrix, because we've worked with lots of matrices. Okay, let's look at a bigger matrix here. Our friend from last time. So if we want to find a basis for the null space of A, I could again, do what I did before and set up this multiplication. Now my vectors here are going to have to be 4 by 1 vectors in order to do this multiplication. So I'm going to x, y, z, and say w. And I'm going to have my 0 vector is going to be a 5-dimensional vector. It's going to be 1, 2, 3, 4, 5 zeros. And then I could do all the multiplication and set it up and then get the matrix, the augmented matrix, and then row reduce. Or I could recall that A row reduces to this matrix, and I can do the multiplication right here. So I'm going to have x, y, z, w. And so again, this is 5 rows by 4 columns, so I would need to multiply by a 4 by something, which is a 4 by 1 in this case, and I end up with a 5 by 1 matrix. 1, 2, 3, 4, 5 zeros. So from here, if we do the multiplication, you get, let me go right into a system because I'm going to run out of room here. So you'd get x minus 2z is equal to 0, that's from that first row, and then you'd get y plus z is equal to 0, and then you'd get z is equal to 0. And those are all of your constraints on this system. So you have x equals 2z, y equals negative z. Z can be anything, it's what they call a free variable, and this should be w equals 0, w equals 0. So I'm going to call z equal to t, so that I'd have x equals 2t, y equals negative t, z equals t, and w, I keep calling w z, equals 0. So all of my vectors, x, y, z, w, look like 2t, negative t, t, and 0, from which I can factor out that t, and I get 2, negative 1, 1, 0. So all the vectors that are in the null space of this matrix are scalar multiples of 2, negative 1, 1, 0. So the set that contains 2, negative 1, 1, 0 as a basis for the null space of A. And so the nullity of A is 1, because there is only one vector in the basis for the null space. And so the dimension of the null space is 1, and by definition, the dimension of the null space is the nullity. And so if you remember, the row space the row space had the basis 1, 0, negative 2, 0. The rows, once you row reduce the matrix, as a basis, are a basis for the row space. So this has 1, so the rank is 3. The nullity is 1. The rank plus the nullity has to add up to the number of columns. So that's a good check on that. So you have a matrix with 4 columns like we do in this case. We could have a rank of 3 and a nullity of 1. We could have a rank of 2 and a nullity of 2, a rank of 1 and a nullity of 3. We could also have a rank or a null space that's got just the 0 vector in it, in which case, like if the null space has just the 0 vector in it, then the nullity would be 0. So that is a relationship that's kind of handy to know about the relationship between the rank and the nullity and the number of columns in the matrix. So that is the null space and the nullity of a matrix. Okay, very good.